We have so far spoken about the general concept of phyllotaxis and geometric canalization, meaning the conserved pattern seen. Now, we will talk briefly about a region in the plant, growing plant, called the shoot apical meristem. Um, Typical scanning electron micrographs represent these typical regions from Arabidopsis as P1, P2, P3, and the angle formed between the regions appears to once more be a golden angle. But what these shoot apical meristems are also is an organ factory. So, in fact, these P1, P2, P3 are all primordia. Meaning to say they are the precursors to the mature organs. In some senses, as the shoot grows, the apical meristem itself appears to split into subregions, which can then branch off themselves. In fact, according to a paper by Fujita and company, plus one, you can find it online. This process of breakup of the shoot apical meristem can be thought of as a reaction diffusion system. So if you consider the shoot apical meristem as a region which is then surrounded by as a region surrounded by the central zone tissue, which in turn is surrounded by the peripheral zone tissue, let's color this so that we know what we're talking about here. In fact, you could by definition also imagine that there is an outer zone, which we will just simply depict as OZ. In such a system, it turns out from genetics, the two genes that are called Wuschel, that is with the name Wus, and Clavata, that is CLV, interact to determine the SAM position in growing tissue. It so happens that you can represent one of the upstream genes, CLV3, as an inhibitor, we'll call it V, which has a diffusion coefficient that is large enough and can go between cells, be transported in other words, transcellular movement, and an activator which is whooshing. We represent by symbol U. It has a smaller diffusion coefficient. And it cannot be transported across cells, as far as we know. U also activates itself by a term AS, and the inhibition of Wuschel happens by a combination of multiple subfactors of the clavata family. So CLV1, CLV2, CRN, and RPK2. In turn, the activation occurs directly by Wuschel. Like what we had described earlier, it is nothing but an inhibitor that inhibits the activator activates itself and the inhibitor, and this has a larger diffusion coefficient, this has a smaller diffusion coefficient. This is nothing but a Turing pattern forming system. So there is already a pattern forming system in the Phyllotaxis system coming out of the shoot apical meristem. But it turns out that in addition, there is something else going on. That something else requires us to spend some time discussing some very classical mathematical ideas. And those are the ones that allow us to think in terms of simple arithmetic, connect to series concepts, and go back to organ formation and their regularity. And this is the Fibonacci series. Let's write down one of these. So 1, 1, 2, 3, 5, 8. I hope you know what I'm doing. I'm taking the initial two values as 1 and 1, summing them and putting them in here. Now I take these two values, sum them and put it here. Now I take these two values, sum them and put it here, and so on and so forth. And I can write this series a bit more. 13, 21, 34, 55, 89, 144, and so on and so forth. In more compact and general terms, I can say that if Fn is the nth term, the series is defined by F1 is equal to 1, F2 is equal to 1, and Fn plus 1 is equal to Fn plus Fn minus 1. That is to say, the n plus 1th value is equal to the sum of the two previous values. We call this equation 1. The same rule can also give other series provided we use different initial values. So if f1 is equal to 1 and f2 is equal to 3, then we get a sequence which looks like this: 1, 3, 4, 7, 11, 18, 29, 47, 76, 123, and so on. This sequence with this definition is called the Lucas series. It is not relevant to us right now, but it is important to know that in the case of Phyllotaxis, a key property is that the sequence of ratios of consecutive numbers has a special property. It converges to something. So let's write it down. So we know the first few easily. 1 by 1, that is 1. 2 by 1, so the higher number by the smaller number, bigger number, smaller number. 3 by 2, 5 by 3, 8 by 5, 13 by 8, 21 by 13, 34 by 21, 55 by 34, 89 by 55, 144 by 89, and so on. We call this 2. In decimal notation, keeping a precision of 10 to the power minus 4, we obtain 1, 2, 1.5, 1.66, 67, 1.6, this, 1.625, 1.6154, 1.6191, 1.6178, and 6182, and so on. One thing you should observe is that the values get closer as we go to higher values towards a particular number, and that is, we call it denoted by the symbol phi, is equal to 1.61803. Right? This, according to many people and funny notations you will find, and if you Google this, is called the golden number. Interestingly, the sequence we said we will not deal with so much, Lucas sequence, whose only difference is in the f1, f2 values, meaning the starting values, also shows the same property of ratios of consecutive numbers. In the series. The golden number is an irrational number, and can be written as phi, with the symbol phi, the Greek letter, is equal to 1 plus root 5 upon 2, which is 1.61803. Now, there are two kinds of interpretation we're going to talk about next. One is the simple geometric interpretation, and the second, which is relevant for our phyllotaxy problem, is the golden angle.